Today we are going to discuss the movement of an object at constant velocity of motion. We are going to observe me riding this bike and track its change in position over time to see if it follows Newton's second law and travels at constant velocity with zero net force. By watching its movement, we will see that the bike seems to travel at constant velocity of motion with a net force of zero, although it is not perfectly adhering to the predicted model. For observations, the bike moved across the Harrison patio. The bike traveled at a near constant velocity on the flat surface. For the model, we use Newton's second law of motion and assume that there is no change in velocity and that it's just average velocity. Some main assumptions of the model are that the initial and final velocity are the same, rolling friction was unimportant. To take the measurement of change in position, we use the size of the bike wheel, a known constant of 26 inches, which was converted to meters for calculations, and mark the distance traveled in the video of the center of the bike wheel as it progresses through time. The time was measured by dividing the video into its individual frames at a frame rate of 30 frames per second. The total time ended up to be just under 1 3/4 of a second. To the movement of the bike at a perfect constant velocity, I created a graph for the predicted graph at the constant slope. This slope was determined to be the arithmetic average velocity, which should be used to determine constant force. Then I plotted both of these graphs, the observed motion and predicted motion, on the same chart to see how they compared. What if we changed where we considered the x-axis 0? Currently, the x-axis shows that change in position was negative, but actually represents the positive change in position over time. However, if we switch the orientation of the graph would simply point in the positive direction instead of the negative, but all the absolute values of position